Okay, good morning, guys. Today we're going to continue with chapter 7, which is part of module 5. So, what we're going to do is we're just going to recap what we did the week before last, because last week we were doing some of our revision work. So, the week before the last, what we did was that we expressed steady state error in terms of the closed loop transfer function. That's the first thing that we did. And then we expressed it in terms of the open loop transfer function g of s. So once we did that, we did a few problems. For example, we did example 7.2. Now we're going to continue with what we're going to be doing this week. And the first of these is static error constants and system types. So this is where we are at this moment in class. So there are two portions here, static error constants and system types. So what we are going to do is we are going to be looking at the first part, which is the static error constants. What are static error constants? And once you have identified those, then we'll go on to what is a system type. Now, if you remember, when we started this chapter, we said that there are basically three types of waveforms that we will be selecting here, right? That is the step, the ramp, and the parabolic input. Now, the reason why we chose these was because the step input provided constant position, while the ramp input provided constant velocity, and the parabolic input is the one that gave us a constant acceleration. So when we learned, we said that for a step input, the error is equal to E of infinity is equal to 1 divided by 1 plus limit s tending to 0 g of s. So this is a calculation that we made. If you look at the first and second videos for this module, you will get those how we derive those outputs. Then for a ramp input, we saw that for a ramp input, E of infinity is equal to 1 divided by limit s tending to 0 s into g of s. And now for a parabolic input, we find that E of parabola is equal to 1 divided by limit s tending to 0 s squared into g of s. Okay. Now we go on to the static error constants. The first of the static error constants that we have is the position constant Kp, right? So the position constant Kp, as you see here, right? The formula for calculating Kp is equal to limit s tending to 0 g of s. Okay, that is the position constant Kp. Then the velocity constant Kv is equal to limit s tending to 0 s into g of s. And then finally you have your acceleration constant, which is Ka, and that is equal to limit s tending to 0 s squared into g of s. Okay, so now what happens is that you can substitute each of these values, Kp, Kv, Ka, back into the original equations that we derived. So if you have a look here, let's just bring these values alongside. This will make our learning a bit more easier. Let's start with Kp, which is the position constant, right? So this is what Kp is. So now imagine what would happen if you rewrite this equation. So E of infinity step would now be equal to 1 divided by 1 plus Kp, because Kp is equal to limit s tending to 0 g of s, right? Similarly, if you look at Kv, you will see that kv is equal to limit s tending to 0 s into g of s, right? Now if you take that in terms of the error for a ramp input, then this is equal to 1 divided by kv, because kv is equal to limit s tending to 0 s into g of s, right? Then finally you have the constant acceleration. So if you take the constant acceleration and then you put it in here, you'll see that the error is equal to e of infinity parabola is equal to 1 divided by Ka, because Ka is equal to limit s tending to the s square into g of s, and that is the error here, right? So we can rewrite the three equations in terms of their static error constants, and this is how they would look. E of infinity step will be 1 by 1 plus kp. E of infinity ramp will be equal to 1 by kv, and E of infinity parabola will be equal to 1 by ka. So this is the static error constants. All right. Now next class we'll be looking at the system type, which is what will be coming afterwards. All right.